All right, Yuta just can't help himself. He just loves throwing balls in the air. This time, instead of throwing it straight up, he threw it at an angle. That crazy kid. And when he threw it from this time he's throwing it from shoulder level. And all we're given is that it's at an angle theta and an initial velocity v. We're doing this problem because I know a lot of you guys really struggled last week when you were given problems that didn't have any numbers at all, and you were just told to solve it in terms of these variables. So I'm going to do that, and I'm going to hopefully make you guys feel a little bit more comfortable on how you do a problem like this. So we're going to be trying to figure out how far the ball travels horizontally, not how far it takes to get to the ground, but actually how far it goes until it gets to its maximum height. So there's a couple different new things for doing this problem. But at the end, we're only going to solve it in terms of theta, v, and any other constants that might exist in nature. That's things like g or like numbers like 2 that are just like constants that don't change depending on how we set up this problem. That would just always be true. So you're allowed to use anything off that list, and I'll probably say this to one or two of you a lot more times. But this menu, theta, v, and other constants, that's like the in and out. Well, in and out's a bad example, but that's like the menu, and you have to get something off the menu, but you don't have to get everything on the menu. In and out's a bad example because they have like their whole secret menu. But anyways, moving on. So let's draw Yuta, that lovely, lovely human being. Oh, he ended up being purple. I thought I made him black, but it decided to make it purple. Purple. We don't judge. So he's throwing that ball from like shoulder height. It's going at some angle. We have the angle there, and it's going to go. So there's the projectile motion. And let's identify the variables that we have in there. The first variable that I'm going to personally identify is I'm going to identify my own variable h. That's for the height that his shoulder is at. Now, I don't know if that's going to come up. I'm just going to identify that that variable exists. Another variable that I'm going to identify is capital H. And that's actually how far it takes to get to the highest point. It's the distance from his shoulder to how high it goes. So if I want to actually calculate the maximum height off the ground, it would be little h plus big H. But in just a moment, I'm going to define my coordinate system with 0 right where the ball starts. So the maximum height to me from 0 is just going to be h, or capital H. Let's see. We also know that the acceleration is going to be downwards, and it's going to be g. And if I'm talking about horizontal stuff, the x that I care about is this one right here. It's how far it is over in the x when it gets in the y to capital H. I think that's all the variables that I need to define. Did I miss anything? Nope, that's everything. So let's identify our coordinate system. I'll do this in purple again. So I'm going to keep my ball, which is conveniently 0 shaped. I'm going to make it my 0 point. Then I'm going to say positive is going to the right, and positive is also going up. Okay, so now that I've defined my coordinate system and I've drawn my sketch, let's start using this sketch to inform my symbols. My initial position is 0 because that's how I defined it. And my final position is what I'm trying to figure out. My velocity in the x direction, I have to go back and let's do that triangle thingy. If this is v, let's try and color code this. I've been trying to be good about that today. This is going to be v sine theta, and this is going to be v cosine theta. You can memorize that. You're totally safe to do that. Or if you want a little bit more of a reason behind it, remember that sine is opposite over hypotenuse. So that's why this is v sine theta. And then cosine is adjacent over hypotenuse. So that's why this is cosine, because it's the adjacent one to my angle. My angle being this angle right here. Okay, so v naught then is I just figured that out. Sorry, v cosine theta. My final speed will also be v cosine theta. Remember that even though it's reaching its maximum height there, that's because it's lost its vertical velocity, but it still has that horizontal velocity. That's going to be a trick question later on. Not a trick question, but a test question, I should say, later, where I'm going to ask what the speed is at the highest point of a projectile. Please don't fall for saying that it's 0 because it still has that horizontal velocity. Later on in the school year, I'll ask if it has any energy at that spot or any kinetic energy, and it does because it's still moving horizontally at that point. Anyways, the vertical acceleration is 0 right there, meters per second per second. In the y direction, we have a initial position of 0 because that's how I defined it, and our final position is going to be this capital H that I defined. We don't have any numbers, so we either pull the variables from the problem or we make ones up that we think we might need. So I made that H up just as a placeholder to help me work through this problem. All right, and then let's see, V naught y. We're going to have the initial velocity be v sine theta. But in the y direction, the final velocity is 0 meters per second. Because max height means that it can't still have vertical velocity because then it's still heading upwards, but it can't already have negative velocity because that means it's already started to descend. So it's right at that point where it has 0 vertical velocity that it's at its highest point. And the acceleration is going to be negative g because that's how I set up my coordinate system. Okay, so we don't know time yet. We're going to have to start with our y equations like we've been doing, but we're actually going to do this differently than we've done it in the past. I don't actually want to use this variable because that's one of the variables that's not on my menu. I'm not actually allowed to use that one. So if I can get away with it, I'm not going to. Instead, I'm trying to figure out time, and I know a lot of velocity stuff. So I'm going to use my second kinematic equation, or my first kinematic equation, I'm sorry. Vy equals v naught y plus at, or ayt. All these subscripts in the y are just to say I'm doing this in the y direction, whereas like the formula sheet has it in the x direction, but it works for any dimension. So with that set up, this is convenient because I know those variables and I'm trying to figure out this one, and I know A. So let's just plug in everything I know. This is going to be 0. That's going to go to G. This is going to go to V sine theta. So let's plug those in, those variables. 0 equals, it's going to go to negative G. V sine theta minus GT. And I can add GT to both sides. That would put GT over on this side, divide both sides by G, and I get time equals V sine theta over G. Now, it's not a convenient coincidence. If you look back to problem number 2, the time that it was in the air was 2V sine theta over G. It's not a coincidence that this is V sine theta over G. A ball will always get to its maximum point about halfway between the two ends. And I say about halfway because actually it's going to be in the air a little bit longer in this case because it actually can fall just a little bit further. But if we're talking from 0 to 0, 2v sine theta over g is always its air time. And you just plug in whatever variable. And then the max height is v sine theta over g. So that 1/2 relationship is sometimes very useful to keep in mind. Now that I know that, the v sine theta over g, I can go into the x direction. And I'm going to still use the x equation that has time in it because I need to figure out the distance. That's what the question's asking. And I need, I have time to help me solve that. So acceleration is 0. It does have a horizontal velocity. It has no initial position because that's how I set it up. So we just get x equals v naught t. Or since I've already been given some of my variables, I can put in here v cosine theta. That's coming from my x equation, and let's do this in red. V sine theta over g. That's my time variable. And this, again, turns into something that looks like v squared sine theta cosine theta over g. There are some ways to simplify this down, but we don't have to. We can actually just leave it like this. This is a totally acceptable answer. Or if you really, really felt like it, it would simplify down, again, using some trig identities that I'll leave you guys to figure out on your own, although it's pretty close to the same ones as the last problem. It would simplify down to this. And I'm just going to add one extra question to this. Even though it's not part of the original question, I'm going to add the question of like, well, what if Yuta threw it twice as hard? What if he threw it with double the velocity that he did before? How much further would it go? And these kind of questions are often very tricky in physics because the instinctual response is, well, it'll go twice as far. But that's not always true, and sometimes it is. So now you just have no idea what to think because sometimes it's true and sometimes it's not true. Instead, when you're trying to solve a question that says, what happened if I did this? You'll take an equation like this that's in pure symbol form, pure variable form, and we'll start changing the variables that the problem set have changed. So if I said, what happens if I double the velocity? I'm going to take this equation and I'm going to double the velocity, but leave everything else the same. So right there where it says v squared, I'm going to take 2, I'm going to double it, that's the v, and I'm going to square that. But the sine 2 theta, that's not changing. All I said is I'm doubling the velocity. So that has a factor of change of 1. It didn't change. The 2g on the bottom, well, 2 is always a constant, so it can't change no matter how I change the problem. And since we'll assume that Yuta is still throwing this on Earth, that's also a 1 because it didn't change. So when I evaluate this factor of change thing that I have here, you see that it's 2 squared and I get 4 out of there. And that tells me that actually this ball would fly 4 times as far, not twice as far. So we'll talk more about this factor of change method, but I haven't done it in a problem yet that I can think of. So I wanted to model it at least once. The big idea is you still do everything to solve it in pure variable form, and then you just plug in the factors by which it's changing, not the numbers by which it changed. Like if I told you he threw it at 15 meters per second and then later threw it at 30, I don't put 30 in, I put in the factor. It doubled. So I put in the 2, and then I put in every factor that changes gets a number, and every factor that doesn't change gets a 1. And then I evaluate that, and that gives me my answer. So a quick sketch for all of the variables here. In the x position, the graph should look like we've been pretty accustomed to seeing. It's just going to go further and further until it stops. In the x velocity, again, it should stay constant at v cosine theta, and it has no horizontal acceleration. In the y direction, the problem is a little bit interesting because it's going to go up, and this is actually where it ends. That's at t. But actually, if we kept it going, this right here is actually where it hits the ground. It's going to go a little bit into the negative based on my coordinate system, and the amount it goes into the negative is by little h, that variable that I made up earlier and never ended up being relevant to our question. In the vertical velocity, it's just going to do something where it goes from some height, um, from some height all the way down. And the only thing that changes is in the last one, example problem 2, its velocity before and after were exactly the same, just like opposite. One was negative, the other one. This one's going to be slightly lower, again, because it spends a little bit more time in the air speeding up. But nothing changes about the horizontal acceleration or the vertical acceleration. It's always negative in this problem. Okay, there you go. Thanks, guys.